Dr. Farquhar is the mission manager of the Near-Earth Asteroid Rendezvous, which I know you are all familiar with. And he has such a long list of accomplishments. I could do one session just on Dr. Farquhar, but rest assured, I'm not going to do that. In the 70s and in the 80s, he was with NASA Goddard, and in the 90s, he's been with the Johns Hopkins University Applied Physics Lab. For myself, I am very anxious to find out about NEAR, and I've had a lot of people come up and ask me questions, and I've told them the same thing, and I see a lot of them in this audience. If you really want to find out about NEAR, come and listen to Dr. Farquhar. To sum up his accomplishments very briefly, all I can say is he generates brilliant new ideas and mission concepts, and I'm very honored to present Dr. Robert Farquhar.
Thank you very much. First off, I'm going to say, listening to the last speaker, I can assure you there are no bombs on the NEAR spacecraft, at least not that we'd like to detonate before we get to the asteroid. We do have a bipropellant propulsion system, which for some spacecraft represents that bomb, and we hope that isn't the case here. Let's see if I can work this thing now. That's the first test. Well, one of the things that you probably know, or you may not know, is that this is the Near-Earth Asteroid Rendezvous mission is the first mission in a series of low-cost planetary missions, which is called the Discovery Program. So the first thing I want to point out is what the guidelines of the Discovery Program are, and this has been set down by NASA and Mr. Golden, that we use launch vehicles of the Delta II class or smaller. This is to keep the general cost down. The development time should be under 3 years, and the mission cost should be under $150 million. This does not include the launch vehicle, however, or any of the operations. And that's an FY92 dollars. I don't know why they don't update this, but this is the way it is right now. Of the missions that are in the Discovery Program, there are 4 of them. If I can get over here a little bit out of your way. There are 4 of them currently in the program. NEAR, which was launched on February 17th of this year. That's going to be followed up by JPL's mission, the Mars Pathfinder, launching in November '96. Then there's a mission to the moon, Lunar Prospector, in '97. And then in early '99, there's a mission called Stardust, which is going to a comet to actually get dust samples from the comet and bring them back to Earth. There will be another Discovery mission that will be selected in June of '97, and of course we're hoping to be one of the winners in that competition, along with many, many other people. Last time there were 28 proposals put in, and they selected 2. Well, back to the NEAR mission, which is what I'm going to talk about. The first thing is that we are not the first ones to think about going to a near-Earth asteroid. This was thought of, about the first serious study of this thing was done way back in 1964. A paper that Science Applications put out. I guess it wasn't called Science Applications then, but Al Friedlander from that organization was the main author. And they looked at various rendezvous missions, and it's interesting that one of the missions that they looked at was a rendezvous mission with the asteroid Eros. After that, for the next 15 years, there were all kinds of publications on missions to near-Earth asteroids, but not much happened. Finally, though, in 1986, they formed, NASA formed a science working group, and they published a report with a recommended payload and a way to do the mission. Once again, not too much happened because NASA didn't have any money in between this time, but in 1991, when they decided to do this low-cost planetary mission sequence called Discovery, they formed a science working group which looked at various missions, and a near-Earth asteroid rendezvous mission was first on their list. Contrary to what you may have heard in other sessions, there was a competition for the NEAR mission, mainly between two different organizations, JPL and APL. They both did studies of this, and finally APL was selected. That happened in 1991, and we were scheduled to go to an asteroid by the name of Nereus, which is about a 1 kilometer object, and we were going to be launching in 1998. But late in 1992, we found out that there was a roundabout way using the Delta Vega flight path to get to the asteroid Eros, which is one of the larger near-Earth asteroids. And it was beneficial from our point of view because it launched 2 years earlier, thereby saving a lot of jobs at our organization. That was also a factor, but not the major one. In '93, we actually got money from Congress to go ahead with this mission, and roughly 3 years later, we launched on February 17th, and we're now on our way. I've been told I have about a half hour or so, whereas I was previously told that I had maybe 45 minutes, so I don't know if I'm going to get through all this. One of the good things about going to Eros is it's one of the largest of the near-Earth asteroids, comparable to typical main belt asteroids. Also, going back one here, this is a very rare opportunity to go there in 1996 because these opportunities come about every 7 years. Well, that may not be all that rare, but it's on my time scale, that's pretty rare. That is, we have to wait another 7 years, which is too long for me. This is another S-type asteroid, and it shows evidence of a regolith. This means that it has dirt on the surface, to put it in a more usual way. Eros Rendezvous, of course, is going to tell us quite a bit about the composition, the density, and the internal structure of the asteroid. You can't get this from just a flyby mission. You really have to stay there for a while, and you have to rendezvous with it. That is, rendezvous in this sense means to go in orbit around it. Now, we've already had some information on S-type asteroids. We got that from the Galileo spacecraft that flew by 2 main belt asteroids, Gaspra and Ida. And both of these asteroids are S-types as well as Eros, but these are from different ends of the spectrum of S-type asteroids. There's also lots of little classifications within the S-class group. Eros seems to be intermediate in between the two that the Galileo spacecraft flew by. A few facts about Eros. Well, one of the reasons I liked it is because it's named after the Greek god of love, and its number, of course, is 433. It was discovered almost 100 years ago. In 1898, 2 people found it on the same day. I find this hard to understand, but in 2 different places, one in Berlin and one in France. You can see that the asteroid is fairly good sized, 14 by 14 by 40 kilometers, whereas most of the near-Earth asteroids are just a few kilometers in diameter. It's an S-class, which I already said, and it goes out a little bit beyond the orbit of Mars. It crosses the orbit of Mars, but does not cross the orbit of the Earth. But it comes very close to the Earth at certain times. And one time when it came very close, around 1975 or so, they probably took more measurements of this near-Earth asteroid than any other one that we know of. These are some of the things that we're going to be doing on our rendezvous mission when we actually get there, when the spacecraft gets there. We'll be looking at the bulk properties, of course, with the imager and various other things, the shape. We'll get the mass by tracking the spacecraft as it goes around the asteroid, and by getting the size of it and the mass, of course, then we can figure out what the density is, what the average density is. We'll want to know details of the gravity field. We'll want to know very accurately what the spin state is. and would like to know if there is or there is not a magnetic field associated with this asteroid. One of the big things, however, that we're going to do by orbiting the asteroid is that we will be able to tell a lot about the composition of it. This is something that's very, very difficult to do on a flyby mission. We're actually going to be there for almost 1 year, so we have ample opportunity to look over things. Now, this is the payload that we're carrying. The two main instruments, not the two main instruments, but the first two listed here, are both run out of Cornell University, which is from the state of New York. And that's the multispectral imager and the near-infrared spectrometer. And of course, our imager will give us images down to 3 meters when we are in orbit around the asteroid. The mineralogy from the near-infrared spectrometer, we should get down to about 250 meters resolution. This is still pretty good. We also have an X-ray and gamma ray spectrometer on board that will tell us all about the key elements. Be able to see if the object is homogeneous or heterogeneous. We have a laser altimeter that will tell us something about the topography. And I already said that the radio science will give us very accurately what the mass is. And we're hoping that there's a magnetic field there, so we carried a magnetometer along. Now, a few words about the spacecraft. Eventually, I'll get to the good part, which is how are we going to get there and what are we going to do? This is a very simple spacecraft. It has no scan platforms. It has the antenna is a fixed antenna. It doesn't have to unfold at launch. It's 1.5 meters in diameter. That gives you an idea of the size of the spacecraft. The spacecraft weighs about 800 kilograms. It's 3-axis stabilized. The only part which is articulated at all are the solar panels, which are folded at launch. Once they open up, they also stay fixed. We have a lot of fuel on board, about 320 kilograms out of the 800. And of that fuel, we have a dual mode system. Part of it is hydrazine only, which is, we have 12 little thrusters all over the spacecraft, and we have one very large bipropellant thruster. This is a mixture then of the hydrazine plus nitrogen tetroxide. Very bad stuff. And we're going to mix that up in space and then fire this engine, but we get a very high ISP out of that. Well, our delta V capability is about 1.5 kilometers per second that we're able to move the spacecraft. And we have quite a bit of solar power, about 1.8 kilowatts at 1 astronomical unit, so that when we get far out, we still have enough to keep everything going and keep the spacecraft warm. A lot of data storage on here also, 1.7 times 10 to the 9th bits. Okay, most of the instruments are on the bottom of the spacecraft right down here. There's one instrument on the top. This is the magnetometer, which is on the boom, just above the high gain antenna. This is very lightweight magnetometer, weighs about a couple of kilograms. The rest of the instruments, most of the weight of the 60 kilograms is in the X-ray and gamma ray spectrometer and the X-ray solar monitor and the multispectral imager. But you can see all these instruments are on the bottom. They're all fixed, with the exception of the near-infrared spectrometer, which can scan plus or minus 30 degrees. A couple other words about the spacecraft. We're going to claim that this is the first planetary mission in the faster, cheaper, better category. We actually had 35 months to build the spacecraft, but it only took us 27. The cost limit that we had on this, like I said before, was $150 million in FY92 dollars. The cost here is in real year dollars, which is $122 million. If you convert this into FY92 dollars, we actually came in about $108 million. And I guess about a month ago, we gave a check back to Mr. Golden of about $3.6 million, which we did not spend. So he put that down. It wasn't me, but it was the project didn't spend its money. I actually spent a lot of money traveling around, so I can't take all the credit. The reason I say this is the first planetary mission in this category. There's been some other relatively inexpensive spacecraft that have been done about the same time, the same cost, but none with as comprehensive a science payload as we have on this one. And also a very redundant spacecraft. We did not compromise and make anything single string. We also go out quite a ways from the sun, about 2.2 AU. That's well beyond the orbit of Mars. And we have to last 4 years in order to complete the mission. Well, now I'll get into what the mission is. This shows the Earth's orbit here going around the sun at the middle. The spacecraft orbit, or spacecraft flight path, is in red. The target asteroids, because we found another one that we could fly by on the way to Eros. They're in green on here. Here's the Eros orbit, coming in like this, going out just a little bit beyond Mars. And then we have another one by the name of 253 Matilda. This is a main belt asteroid which we found out very late in the game, and we came close enough to it that we could deflect our orbit just a little bit, and we were able to fly by this asteroid. Okay, here's our launch back in February 17th. We're now out, in here somewhere. And we go out to whoops, I got the wrong path here. We go out to 2.2 AU about here. This is the furthest distance we ever get from the sun. Then in June of next year, we're going to fly by this main belt asteroid, and 1 week after that, we fire up the biprop engine for the first time. This makes a rather large change in our orbit, which lets us come back to the Earth again here in January of '98. And the purpose of this is that we increase our energy relative to the Earth, because when we make this burn way out here, we actually decrease the perihelion, so we cross the Earth's orbit rather than coming in a tangential way. By doing that, by coming in with a higher energy, then we use the Earth's gravity then to change our inclination so that we basically match the inclination of Eros orbit. That lets us come in at a very low flyby speed, or very low velocity relative to Eros at the time of the intercept, and it means that we can use less fuel when we go into orbit. This is why we were able to do this on a Delta rocket. This is to prove that we did launch. This picture has not been faked or anything or touched up. This is Delta rocket number 232. I was happy to see that it was number 232 because 12 is my lucky number. Because on another mission I worked on, which is the IC3 mission, that launched in 1978. We launched on August the 12th, and we launched at 12 minutes and 12 seconds after the hour on Delta Launch Vehicle 144. So that was good. Then I thought, well, how can this one be good? You know, this is 232, but then I can see that if it's 2 times 3 times 2, I get 12. So I knew we were in business. But nothing would go wrong then. Okay. Here's 1996. This is what actually, 1996, we really don't have very much to do, as you can imagine. It's not until 1999 until we get out to Eros. But we did our launch, and we took some pictures of the moon right afterwards to calibrate the imager. This was on February 20th. Now, these aren't the kind of pictures we want to put on the front page of the New York Times, but it did show that the imagery worked quite well. We also, when we took out the launch errors, we did that on March the 2nd, and the launch was so good, we had budgeted about 50 meters per second here, and we only needed 9 meters per second to take them out. We did some imaging of Comet Hyakutake on March 24th. Once again, I don't want to publish those pictures anywhere, but they are on the website that we have for the NEAR mission. This was strictly for calibration purposes. We were about 1/10 of an AU from the comet at the time. We have just finished our instrument checkout. That was done in April and May. And the next big event coming up is the next TCM2, which is about 1.5 meters per second. That's on August 21st. Now, for the rest of the year, though, we have to prepare for what we're going to do next year, which is going to be very complicated. That is our first flyby of an asteroid, which is not Eros, but 253 Matilda. And I do have something on it here, because most of you probably haven't heard of this one. Well, it was discovered in 1885 by somebody in Vienna, who for some reason named it after the wife of the guy that was the deputy head of the Paris Observatory. I don't know what the reason is. Maybe they were downsizing in Vienna and he's looking for a job in Paris. I don't know. But anyway, you can see it's quite a large asteroid. 50 by 50 by 70 kilometers. Now, almost nothing was known about this asteroid until we decided to go there, and then all of a sudden everybody started looking at it, and they found out some very interesting things. First thing they found out was that it was a Type C asteroid, which is carbon rich. But the most interesting thing is they found out that its rotation period was extremely long. It wasn't 17 hours. It was 17.4 days long, so it's basically not rotating. Some information on the orbit. Perihelion, we're getting it very close to its perihelion point, and its inclination is not very large. Our flyby speed is roughly 10 kilometers per second. We're coming in at a very bad phase angle. It turns out that our imager can look within about 38 degrees of the sun without getting a lot of stray light in there. So we're very fortunate because we're just outside of that area here. We come within about 40 degrees of the sun. And the closest point that we get is about 1,200 kilometers. I chose that number because, like I told you, 12 is my lucky number. I have a view graph here that Clark Chapman put out. He's a member of our science team. So I'm not going to be able to answer all the stuff about this, but he says that there's only one chance in a billion that an asteroid could be spinning as slowly as this one is. There are two others like this. So he says something seems to be damping the spinning motion. And you can read some of this, I hope. And he says, well, it's a big mystery. I mean, he doesn't understand what the process is, and nobody else seems to either. So hopefully, when we get some pictures of this thing, as we fly by, we'll be able to shed some light on this mystery. Here's some other things about the Matilda encounter sequence, and I'm not going to read all this except the things that this shows is that the whole encounter will last about half an hour, and we're going to get quite a few images. There's actually several hundred images here, of which most of them probably will be of the black sky, because we don't know exactly where it is when we fly by. So there will be quite a few of them that were very up close. Well, we were talking about 196 pictures when we were within about 3 minutes of the flyby. And then later on, towards the end, we're going to try to look for some satellites, since Galileo found the small satellite Dactyl going around the asteroid Ida. Okay, this gives you a better idea of the size. These are the asteroids that are shown here in white. This is Ida. These were both seen by Galileo. And then here's little Dactyl down here, about 1 kilometer in diameter. Eros, you can see, is somewhat intermediate in size between these two. We know roughly what the shape is. And this one, this main belt asteroid is quite a bit bigger, as you can see. Here's 10 kilometers here. So we think even with the flyby, we'll learn quite a bit about this one. Although I have to say that our imager really is not built to do flybys, and we have to turn the whole spacecraft as we go by. And that's why we have to fly by at around 1,200 kilometers, because we can't turn the spacecraft fast enough to keep up with it. Also, the resolution won't be quite as good as the Galileo spacecraft did. Once again, because the camera was optimized for the Eros rendezvous phase. Well, after we do our flybys and we hopefully fire the biprop engine, we are then going to do a swing by of the Earth, and this is what that looks like. On January 22nd in 1998, these are the changes we make in the flight path. The main thing is to change inclination, like I said. We'll come in over the North Pole of the Earth, and one of the interesting things here is that we're going to get a very good view of the Antarctic continent, which will be in sunlight at that time. And we're hoping to take some pictures that have never been taken before, seeing the entire continent. This is a side issue of the mission, of course, but we like to get some extra science out of it if we can. Ultimately, we will get to Eros, and this is a picture done by Pat Rawlings. Let's see if I can get this in. Well, if Eros looks this interesting, I can't wait to get there. There's some nice craters on here. This shows our spacecraft in orbit around there, and you can't see it here, but there's a very small U.S. flag on the side here. He wasn't sure whether to put that on or not, and he asked me about it, and I said, yes, we ought to have a U.S. flag on there because we'll probably try landing on the asteroid at the end of the mission. And but the project manager would not go along with that, so we do not have a U.S. flag on there, but we do have one here, and it's painted. Not quite as good. On the other hand, we have some other interesting artifacts on the spacecraft, which I can't tell you about. Probably already said too much. This shows you what our timeline is when we're about ready to rendezvous, and it takes us about 1 month to complete all the rendezvous burns with the biprop engine, and we end up then flying by around 5 meters per second, just barely going by on the sunward side at about 500 kilometers. And the reason I've outlined this date, so that's the benchmark date that we use to start our Eros mission. It also happens to be my wedding anniversary since I planned the mission. I did it that way because after all, we're going to Eros. It's a God of love. Let's see. Yeah, we're going to start out in a high orbit, about 200 by 400 kilometers, come down to about 100 kilometers circular, then eventually get into the prime science phase of the mission, where we get into an orbit about 35 by 50 kilometers. This means that we'll come within about 15 kilometers of the surface at that time. So actually pretty close. Time isn't too bad. Here's a couple of things about the orbital periods. You know, going around the Earth, we go around about 7 kilometers per second. Well, here we go around, even when we're in a low orbit, we go around 7 meters per second. Very small object, but it is possible to orbit it. And actually, the sphere of influence of this small body goes out about a couple thousand kilometers. This is all based on our density of 3.5 grams per cubic centimeter, which may not be right. It could be anywhere from, well, this could be off by a factor of 2, actually. this is one of the things that we hope to learn, is to just what the densities are. You heard the previous speaker talking about deflecting some of these asteroids, so it would be nice to know roughly what the densities are of an S-type asteroid, and as a matter of fact, for all the other asteroids of the different classes. This is showing us in our science orbit. This is the orbit as viewed from the sun. If you were sitting on the sun, the orbital plane is always within about plus or minus 30 degrees of this, so our solar panels will get enough power. And this shows the spacecraft, not to scale, and the instrument's pointing towards the asteroid. As it goes around its orbit, the spacecraft will roll to keep the instrument pointing at the asteroid. The asteroid's also rotating. Now, there's two different ways this works, and that is in April of '99. This is early in our mission. The rotation axis is lined up and is pointed towards the sun. That is, the south pole is pointed towards the sun. So the asteroid is rotating under us, and half of it we won't see because it's in the shadow all the time. But later on, as Eros goes around the sun and our orbit is still saying roughly perpendicular, that is, the orbit plane is roughly perpendicular to the spacecraft Earth line, the asteroid will be coming and rotating around this axis, which is kind of in the orbit plane, and then we'll be able to see all sides of it. That is, the object will be rotating out towards us. You may not pick all this up here. We have a little video that we can show you during the break that'll show you how the asteroid rotates under the spacecraft. Well, to sum up, one of the things that we're happy about is I think we're doing quite a few firsts on this mission. This will be the first time that any spacecraft has orbited a small body. First in-depth exploration of a near-Earth asteroid, and the first reconnaissance of a C-class asteroid. Other things that kind of are of interest to people in the business anyway, maybe not anybody else, is this is the first planetary mission for the Delta launch vehicle. And they pulled it off quite well, where they had to aim for a certain point and a certain object. This will be the first time a spacecraft powered by solar cells is operated beyond Mars orbit. The record right now is something that's in orbit around Mars. And it'll be the largest asteroid visited by a spacecraft thus far, 253 Matilda. A word about the future leading into some other talks here. These are the missions that are currently on the books, the ones that have flown and the ones that are scheduled to fly. We have Galileo that has, in 1991-93, has flown by 2 S-type asteroids. We have NEAR with the flyby in 97 and the rendezvous in 99. And then in between those, if all goes as planned, Clementine 2 is scheduled to fly by 3 of the near-Earth asteroids in 98, and then the final one in 99. And then there's a technology demonstration spacecraft called Deep Space One that JPL is flying that will fly by another near-Earth asteroid named after the teacher astronaut. And then finally, the Japanese have a very ambitious engineering mission, actually, that is scheduled to get a sample of a near-Earth asteroid, bring it back to Earth again. This would happen, it will launch in January 2002. It takes about 2 years to get out the asteroid, about a year there, and then it comes back to Earth again in January 2006. So we may actually see what some of these things are made out of. This is Nereus, which is a Type C asteroid. And just in the last couple of weeks, we started looking at a follow-on to the NEAR mission. You know, any mission worth its salt, it's always got to have a follow-on. We're looking at trying to fly a copy of the NEAR spacecraft out to a Type V type near-Earth asteroid. There's only 3 of them known so far. They're called Vestoids because they're believed to have come from the main belt asteroid Vesta. They think that they're chips off of this one. So we figured out a way that we could rendezvous with it. We would launch in October '99 and get there in 2001, and the end of the mission happens to be on my birthday again in 2002. Well, that's about all I have to say, except to show you one thing. We put out a special philatelic cover, and of course, since we're going to Euros, there was a perfect stamp that the U.S. Post Office put out for this. You see basically with Euros on the stamp. So we're hoping to have extra covers that we can put out when we actually get there. Thank you very much.
Since we only have one speaker, I really do want to thank Dr. Farquhar, and we are going to open it up for questions. And I'll let you handle your own question and answer, Bob, since there's only you. But I want to mention, I'm an accountant, and when somebody talks about a project that comes in and gives money back and is done early, he deserves another round.
I can't believe there's any questions. I thought I told you everything. No. I can give it to you. I'll give you my card at APL, but I don't know what the address is.
It's in the envelope.
Next. So, yeah.
There was, I believe it's Euros, the current issue of, or a couple issues back with Nature, there's a dynamics group in Nice, this obviously observatory that discovered this thing, and they've done long-range numeric integrations of this particular asteroid thing. And they have shown one possible, it becomes very chaotic after about a million years. It does various resonance interlockings with the Earth, Mars, etc. And one possible path they have determined is that it does collide with the Earth about 3 million years from now.
Yeah, Euros. Well,
Yeah.
yeah, I have heard that one also. I think Don Yeomans from JPL worked it out as well.
Could you repeat the essence of the comment?
Okay, I guess the essence of the comment is about 3 million years, you say? It's supposed to...
Roughly, something like that, the exact number I don't have.
Well, roughly it's 1 to 3 million years. It doesn't make much difference to us anyway. But this asteroid is supposed to come back and collide with the Earth. So we have to figure a way out prior to that time to deflect this thing. Yeah. No. No. Well, I mean, yes and no. We have a navigation team from JPL that is part of our team. And I don't often think of them as being part of JPL since we all work so closely with each other. And they've been working on the navigational aspects of our being in orbit around Euros. It's a lot more complicated than anything we've had up to now. There's no doubt about that. But it's certainly doable, and we expect to do it. And as a matter of fact, at the end of the mission, we were talking about coming in a lot closer, maybe about 1 kilometer off the surface, and getting some really close-up pictures. And then we're also thinking about landing on it at the end.
If you actually land on it, would you still be able to communicate with Earth or not?
No, probably be a crash landing, a ranger type landing, if you will, and then take pictures on the way in. But I don't think we'll last too long on the surface. First of all, it's going to be difficult for us to do a soft landing since we're really not built to do this. Although we are thinking in terms of uploading some new software or some, so that we can come in as slow as possible. But I think we're still going to hit pretty hard. And since our panels are fixed and everything, and we have a fixed antenna, it's going to be very difficult to communicate back to the Earth once we're on the asteroid. Yes. Yeah. Well, it depends on which way you're looking at it, yeah.
Possibility of that, if you were to find that at the end, might have to make this a bit easier.
Well, it'd be easier to land on one of the poles, probably. No, right on the spin axis. Right on the spin axis, the part that isn't going end over end, so to speak, right? Yeah, it's moving a lot faster than we are, especially if we get down lower. I mean, we're not going to be synchronized with it.
Is there another possibility we actually will see those flybys using California target for some random other function asteroid rendezvous flyby with 2 years flight time?
Well, yeah, the question is, can we get out of Eros orbit and then find some other body to go to? And the answer is we don't have enough fuel to do it, I'm sorry to say. With the asteroid we were looking at prior to this, we were going to go to Nereus and we were going to rendezvous with that. And there it only took 70 meters per second to come back to the Earth again. And I could use swing bys of the Earth then to get out to several other objects. That would have been fun that way, but I think Eros is a more interesting asteroid. It's a lot bigger.
The idea of follow-on missions. Are any follow-on missions considering using the new ion engines that will be demonstrated in the Millennium to produce the capability for multiple flybys in spite of high revenue requirements?
Well, as a matter of fact, Deep Space One is going to test out the ion engines that NASA plans on using in its Discovery missions of the future. It's an N-Star system, I think it's called. And the Japanese are also doing an ion engine mission to get the sample back. There's no other way that they could do it. So yes, the answer is yes, that they are looking at this, but they're only going to one body each. Yeah. Well, the question is, there's a lot of empty space, and how are we getting to this main belt asteroid? And we know exactly where it's at. We're not going to swing, well, we're going to fly by it. It does turn out, though, and I forgot to mention this, of the two previous asteroid flybys, they were not able to determine the mass of the asteroid from the radio tracking because they were much too small. This thing is roughly 10 times more massive than the other ones, and we're going a little bit closer. So we expect to determine the mass of this body to about 4% accuracy.
I'm wondering, was it the low cost, or what, how did you decide to use hydrogen peroxide instead of an iron or anything on this situation?
The question is, why did we pick the kind of propulsion system that we did? Yeah, it was cost more than anything else, although I guess risk would be another factor here. By using an ion engine, it's an untested sort of thing. It would cost a lot more, and it would be deemed a little bit more risky at this time. Does that answer your question?
Why you chose to run with the girls
Well, because it would take too much delta V to rendezvous with any main belt asteroid. That's a very difficult thing to do. They are talking about trying to do this in one of the Discovery proposals. It takes quite a bit more delta V and a lot more time, and they need to swing by Mars and so forth. It's complicated. Plus, you also need a lot more power when you're out at those distances to operate all the instruments and everything. When we're out at 2.2 AU, all of our instruments have been turned off, so we have a lot more power margin in there. Oh, sure. Yeah, I guess, yeah, we're going to show the video. It only lasts 10 minutes, so If there's no further questions, I don't know how you're going to.
Thank you, Bob. Let's have a really